that he used Midas Gen for.
Good morning, everyone. I am Engineer Adam C. Abinales, Principal Engineer of Abinales Associates, Engineers Plus Consultants. I am going to present to you in this today's Midas Gen Expert Academy Forum the application of the software Midas Gen, in which we use this for a case study project. And we did this simulation of an existing building wherein we have to do some seismic analysis. And then we use actual ground motion data and compare these results with the design basis earthquake based on the NSCP 2015. Well, basically the building was actually designed using the previous edition of the NSCP, though considering that the earthquake loads provision of the NSCP since 2001 until 2015 are basically the same. So I'm going to present to you the seismic analysis features of Midas Gen for linear analysis, both response spectrum and time history. The presentation outline would be as follows. I'm going to show to you the modeling parameters, the materials input, the loads input. Then we did the structural analysis, first doing the modal analysis. And then we did the time history analysis using actual ground motion data obtained from earthquake recording instrument. Then we compare it with the response spectrum analysis based on NSCP 2015. Now, okay, this is actually an actual case study for a 10-story reinforced concrete building of a spatial moment resisting frame. Last year, April 22, 2019, magnitude a magnitude 6.1 earthquake hit Central Luzon, and the ground shaking was felt here in Metro Manila. Well, considering the epicenter of that earthquake is somewhere in Pampanga or Zambales, the shaking there is about intensity 7, and here in Metro Manila, the shaking was felt considering intensity 4 or 5. So the earthquake struck Central Luzon at around 5 o'clock and 11 minutes in the afternoon, and the duration of the ground shaking lasted for 27 seconds. Now here's a video taken from a YouTube of that of a certain supermarket building in Pampanga. You could imagine that again, that around 5:07 and then 22 seconds, then in about 4 to 5 minutes, the CCTV signal went out. So that means something happened to the building already. And ergo, as we all know, that's a supermarket, was chosen supermarket about 2 to 3 story building that immediately that collapsed immediately after about few seconds of ground shaking. Now this is another video taken during that same event. And you could just imagine that here in Metro Manila, no, the shaking was felt, and then a lot of people went out of their buildings because of that ground shaking. Well, considering those earthquakes, no, that if we are going to look at um, the earthquake events, no, that have struck a lot of countries in the world. Now, Philippines rank number 6, wherein we do experience around 337 ground shakings, of earthquake events, um, in a year, no? Or rather, from 1900 to 2019. And then, of course, as you can see, Indonesia ranked first, wherein it has experienced from 1900 to 2019 of 852 major earthquake events. Now, what you see on the screen are the floor framing plans of the 10-story reinforced concrete building. And then you have the foundation plan. You have the second floor framing plan. Then you have the third floor framing plan. And of course, the typical floor plan from fourth floor to the 10th floor. Well, this is not actually a regular building considering the shape of the building, but just the same, looking at the framing, they seem to be of, a certain regularity. Well, basically, these plans are, according to the source, are the as-built construction plans, which we use in doing the modeling of the existing building. Now I'm going to show to you the modeling parameters. First, of course, we define the structure type. This is a three-dimensional structure, and we model it as a special moment resisting frame. Basically, the codes that we considered in the simulation study are the NSAP 2015. And as we all know, the structural concrete provisions of NSAP 2015 is reference to ACI 318-14. Then the earthquake load provisions in the NSAP 2015, section 208, is actually reference to UBC 1997. Based on the structural plans that we have, the materials considered in the analysis, the concrete is 3,500 PSI, whereas the rebars are considered to be conforming to ASTM grade 420. Part of the modeling, we considered stiffness factors for the section modifiers of beams of 0.35 EIG and the columns 0.7 EIG. Now we analyzed the frame having fixed supports at the top of the pile caps. Well, the building, based on the foundation plan, is sitting on piles. Now, considering that the location of this building is somewhere closer to the Manila Bay. And of course, the building is actually part of the central Manila, wherein the soil condition there is predominantly SE. Now the group dumping, we assume we consider the 5% for reinforced concrete, considering the inherent dumping of the reinforced concrete to dissipate the energy from the ground shaking. Then the loads Of course, we consider dead load, live load, and earthquake load. Now, just for the sake of doing this study, we consider the actual loading based on the um, present occupancy of this building. So the dead load and the live load are all defined using the actual occupancy of the building. And for the earthquake load, for us to be able to compare the actual ground motion data to that of the design basis earthquake used in the design of this building, no, by the original designer. So we use the response spectrum analysis procedures, considering linear dynamic, as well as the time history, also considering linear dynamic procedure. Then, of course, for the eigenvalue analysis, we did a subspace iteration. For the materials input, using the Midas Gen software, so we have the properties, and then we identify the material properties, and then we add these materials. No, you are going to have an actual hands-on. I think scheduled later within this week, and then I will just be simply showing to you some of the screenshots that we took, just for us to you, for you to have a guidance on how we go about Midas Gen as a tool in doing this case study. So we added the material as concrete, no, and then of course the type of the design is reinforced concrete, and then the standard as part of the inputs in Midas Gen, you have the ASTM reinforced concrete, and the concrete grade is defined as C3500, meaning the compressive strength of the concrete is 3,500 PSI. Then we input the loads. First, we have the static load cases. Well, definitely, as part of the static load, you have the dead load, the live load, well, the earthquake load, and the roof life load. No, since the 10th floor is actually a penthouse, and it is on a roof deck, so practically what we are going to input there are roof life load. No, aside from the roof life load on the penthouse structure at that 10th floor. Then again, as part of the loads input, no, for the self-weight of the entire structure, no, wherein the self-weight is treated as the dead load, no, then the weight factor is negative 1.0 along the Z direction. Then these loads, the dead loads, are converted to masses in all directions, the X and the Y and the Z direction, for to be able to capture the seismic weight and to be able to consider these masses as part of the earthquake analysis. Then all load types selected for conversion, no, as you can see here. And then the load factor used for the dead load is 1.0. Then we did a run, no, doing the model analysis, and then we came up with these results of the model analysis, wherein on the first mode, you get the structure period of 1.4518 seconds. Well, as we all know that we can actually do the method A of estimating the structure period using the formula prescribed in the NSCP, section 208.5.2.2. And then using method A, depending on the structural system, in this case SMRF, then you can calculate or rather estimate this structure period using that formula equation 208 plus 12, wherein you have the period equal to cis of t multiplied by h of n raised to the 3/4. Now, basically, the results that you see on the left is actually the run, no? And that is the method B, wherein, of course, method B would calculate the fundamental period, considering all the properties and deformational characteristic of the elements, no, of the structure. Well, one thing that you need to understand that when you compare your method B structure period to that of method A structure period, that the value of the structure period obtained from method B shall not exceed the value 30% greater than that of the structure period obtained from method A. So, well, of course, you have to do that check so that you will be able to satisfy that particular provision of the code. Then definitely, you do the structural, or rather the mathematical model of the physical structure that will somehow represent the spatial distribution of the mass and stiffness of the structure, so that this mathematical model, no, wherein you have this structure period computed using method B, then you will be able to arrive at a certain number of modes in your model analysis that you must be able to obtain or attain at least 90% of the participating mass of the structure in the calculation of the response for each principal horizontal direction. So in this case, practically using a number of modes of 15, we are able to get, no, more or less close to 90%, no, for the X and the Y direction. Well, of course, these are the two principal horizontal axes. Then these are the animation of the deformed shape of the structure, considering the different modes of vibration. So mode 1, which is the fundamental mode. Then if we try to look at the deformation, no, animation of mode 1, the vibration is in the transverse direction, whereas mode 2 is in the longitudinal direction, whereas in mode 3, you already have the rotational displacements already. Now, let us proceed to the analysis procedure based on NACP 2015, section 208, 5.3.4. As prescribed in the code, no? Now, basically, the code only provides for the linear dynamic analysis procedure. So meaning that when we analyze our structure and we design it using these procedures, we are considering that the analysis of the structure and whatever response or behavior of the structure would be within the elastic range. So using the response spectrum analysis per section 208.5.3.341, that you do an elastic dynamic analysis of the structure utilizing the peak dynamic response of all modes, having a significant contribution to the total structural response. Whereas section 208.5.342 is about the time history analysis, wherein the analysis of the dynamic response of the structure at each increment of time when the base is subjected to a specific ground motion time history. Now, in this particular case study, the data that we obtained from the earthquake recording instruments, which is installed at the ground, serves as our source for using that ground motion time history as an input to this time history analysis. Now, let me start with the time history analysis. So you have this as one of the screen menu in the time history global control on how you are going to input the earthquake ground motion data into the Midas Gen. So you have to open the time history global control, no? And then you have here to define the geometric nonlinearity, no? Specified as none, because since we are doing the linear analysis. Then we consider static load scale factor, which is set to the reciprocal of the response modification factor, R. Now, since we have a special moment resisting frames as given in table 208-11A, the response modification factor R value is equal to 8.5. And then we get the reciprocal of that as an input here for the static load case for all the loads, no? Dead load and life load, and then the earthquake loads in both directions, X and the Y axis. Then we define, no, the time history load cases. So the analysis type would be linear. And then the analysis method would be modal. And time history type would be transient. Well, basically, it is a transient load because the earthquake that happened in April 22, 2019 is considered to be a transient load, no? Because it doesn't happen all the time. No? Well, basically, earthquake load is actually a transient load. Now, the end time is about 60 seconds based on the data that we extracted from the earthquake recording instrument. Actually, I'm going to show you the raw data, no, later on, that when we extract the readings of the ERI on that particular day of April 22, 2019. So we have to put there end time of 60 seconds, although actually in the raw data, we had about 100, almost, I think 200 seconds. But definitely, you only have to consider, since I think the shaking, the duration of that earthquake, as presented in the first part of my presentation, was about 27 seconds. Although we have to do some filtering and then truncating of the ground motion data so that we would be able to get more or less the time history data that you are going to use in this Midas Gen input. So the time increment is 0.01 second as per data extracted from the ERI. And the damping ratio is inputted as 5%. Okay. Now you have here the summary of that load case as already defined. Now, this is the ground motion data extracted from the earthquake recording instrument, or the ERI. So there are about 6,000 data points, no? From 0.01 second to 60 seconds with an increment of 0.01 second. Okay, and the data gathered from the supplier of that ERI, which is Infinity One Global Tech, Incorporated, and they have these sort of a part of their brochure, no, indicating some analytics, no, or some data for the guidance of the user of the ARI, as well as the engineer who's going to interpret the results. So you have the ERI, and then you have the modified Mercalli scale. Now, based on this one, it will register more or less the ground motion, or rather the ground acceleration at the time of that event. And then more or less it will give you an idea on what is the earthquake intensity, no? The modified Mercalli intensity scale. So the acceleration value is recorded as 36.8 gauls, and divided by 981, that will give you about 0.036, no? So if you're going to look at this ground motion, no, 0.036 G, it's way below, no, the minimum ground acceleration, or peak ground acceleration that we use in our design, no? So considering Metro Manila or Manila is in zone 4, so the minimum ground acceleration that we use in our design is 0.4 G. So we do expect that this building would respond, no? And perform well, no, during that event. Well, anyway, this somehow gives you an idea on what is the intensity scale at the location, at that particular location of the building, which is intensity 4. And the source file coming up with these acceleration values is actually the waveform, no? Extracted from the instrument, no? Dated 2019-04, 22. That is the date, and 17-16-03, and that is the time, no? Meaning 17 hours, meaning 5 o'clock, 16 minutes, 3 seconds. Now, so using those data, no, the earthquake ground motion data, then in the Midas gen, we open the time function. Then you will note here that you have these time functions. You have to add that time functions, and then you define these forcing functions in the north-south and the east-west, no, which is the horizontal direction of the instrument, no, registering the north-south and the east-west directions, and of course the vertical acceleration, which is represented by up-down. And these are the raw data, no, from the waveform file that we extracted from the ERI. So as you can see, this is the raw data. Then we did plot the graph, no, representing all these data here that we obtained. So we have here the first column would be the period or the time or the ground shaking period, and of course in the north-south direction, and then the east-west direction, and then of course the up-down. So it's very important that the instrument, no, that you that the building must have, no, must have these triaxial directions. Okay, so this is the up-down direction, and then continuing with the raw data that you see. So this is all less than 1 second. Still, we have to get, as you know, all the recorded readings from that instrument up to up to 120 seconds. No? So then basically you only need to do truncating so that you get the time history data that you're going to use as your inputs into the Midas gen. So this is the north-south direction, no? Then this is how we input it. So you have to do this add, modify, show time history functions. Then you have the function name north-south, and then of course that will have to be defined as a time function data, normalized acceleration, and then use the scale factor of 1.0. Okay. Then this is for the east-west direction. And then the same procedure that you have to add, show these time history functions in the east-west direction. Well, basically, these input here are taken from the raw data, no, as truncated, so that you will be able to get, no? Of course, start with before the ground shaking starts, and then when the ground shaking already happens, and then you have this time history data. Now, this is for the up-down direction. No? Same thing that you got this information from the raw data of the ERI. Then you define the function for the direction x, no, one at a time. Okay, so for the function for direction x, no, that is the east-west direction, and then you define also the direction for the y, let's say north-south direction. So you have to take note of the scale factor here, 1.0. And then you do the same for the up-down function. So you define the scale factor there as 1.0. Then, of course, we did the run. Oh, by the way, when we did this modeling, you have to prepare two models actually. So basically, you have to prepare two models. One considering the time history ground motion data, and the other one is, well, using the response spectrum. You cannot input these two earthquake data in one single file, no, wherein you will have to run it one at a time. No. So what we did is we prepared two models. No? So in that case, we run it, no? And then we get the results, no? In particular the displacements at every floor, so that we'll be able to check the lateral drift of this existing building. No? And then we compared that drift at every floor to that of the drift when you run it using the response spectrum. Well, this is just to, the purpose of this run is actually to make a simulation on if there is really that, you know, significant movement of the entire building when during the ground shaking. So these are the analysis results, no? For the displacement at all floors up to the 10th floor. Okay, so looking at the 10th floor, no, and then you will see that the maximum displacement is recorded at around at a value of 0.003.32, which is 3.2 millimeters. So as you can see, it's very small, no? So this corner, wherein you have the red color, represents the maximum displacement at that corner. Then this is at the roof level of the penthouse. So here it was increased to about 0.0034 or about 3.5 millimeters. Okay, now we did the run using the response spectrum. Well, basically, of course, when we talk about response spectrum, this is based on the design response spectrum as prescribed in the code, no? Well, I would like to think that when this building was designed using the response spectrum as prescribed in the NSCP, whether it is it was a 2001 edition of the code. Then we expect that we have the same seismic parameters as we use in NECP 2015. So for the inputting of the response spectrum data, so you have to add, modify seismic load specifications, of course, for both directions, and then you specify the local code. Now, since the earthquake load provisions of NECP 2015 is referenced to UBC 1997, so we use UBC 1997 as the local code. Then, since the structure is on piles, we assume a soil profile type SD. And then the zone factor is, of course, in zone 4. And then we assume, no? Maybe, no? During the time that when this building was designed, so looking at the possible movement of the West Valley Fault, no? That could generate a magnitude 7.2, so the seismic source type would be A. Okay, but of course, the earthquake of April 22, 2019 in Pampanga will not directly hit this building, no, because it's too far from the source. Okay, but then the nearest active source would be that of the Valley Fault, or even you compare it with the Manila Trench, still far, no, because Manila Trench is about 200 kilometers away, whereas the West Valley Fault would be about within about say, as you can see here, is about 8.5 kilometers, no, less than 10. And the building is considered to be importance factors 1.0, although this building is practically an office building with some floors, no, being used as school, no, or meaning classroom occupancy. Now, the computed structure period based on analysis, no, using method A is 1.45 seconds, whereas of course using the method A, no, the computed structure period or estimated structure period is 0.95 seconds, almost 1 second. Okay, and then of course the ductility coefficient R, or response modification factor R, is 8.5, being an SMRF. Then for Midas Gen to be able to generate the design response spectrum, now after inputting all the coefficients, no, attributed to the distance from the source, no, the soil profile type, and so on, then you will be able to get the seismic coefficients of 0.36 and 0.54. And then of course for seismic zone 4, okay. And then we have to do some modal combination control, wherein the modal combination type would be SRSS, or the square root of the sum of the squares. And then we input the damping method, no? And then of course in this case it is all about 5%. Of course you have to indicate that for the damping method you have to consider strain energy proportional. Okay, so you have the load cases, no, for R as major in the X direction, and then of course you consider ortho in the Y direction, meaning 100% in the X direction and then 30% to the Y direction, and vice versa. And then we did the auto search as enabled in the software, and then we inputted that scale factor of 1 over R, and then of course the modal combination control is SRSS. And this spectrum function would be based on the UBC 1997, also as prescribed in the NECP 2015, section 208. And then we apply the damping method enabled. Then the damping method, strain energy proportionality, and then of course correction by the damping ratio as also enabled. And then that would somehow give us an interpolation of spectral data, no, in logarithm. And then we also included the accidental eccentricity. Okay. So for the post-analysis results, no, wherein we have this excitation angle, which is calculated by the program itself, no, as since we toggle the auto search angle, no, and then this will give you these post-analysis results. Okay. So this is for the for the XY direction, wherein for the RS major, whereas for the RS ortho is 84 degrees. Then we allow the auto generation, no, of the load combinations, no, but definitely since we specify concrete there, and then of course we specify 318-14 as the code, the local code or the reference code, and then we apply the orthogonal effect rule, no, 130, and then we did some scaling up of the response spectrum dynamic analysis, which is very important, no. So here we have to get the static story base shear, and then we get the story base shear, no, based on response spectrum. And then whatever would be the ratio would then be applied, no, and then run it again so that you get these modification factors, no, scale factors. Okay, so I think, well, that rule is prescribed in the section 2085354 of the NACP 2015, which is all about reduction of elastic response parameters for the design. Okay, then we did the post-analysis results, no? So based on static base shear at the ground level, we obtain about 9,199 kilonewtons base shear. Whereas, of course, here, this is the static base shear. And then for the dynamic analysis, for the response spectrum dynamic analysis, now this is the computed base shear. No, as you can see here, it's in the x direction. It's about 6,387.5. No, in the x direction. And then, of course, we apply that scale factor. No, the static base shear divided by the response spectrum base shear, and then we run it again so that we'll be able to come up with these analysis results. So these are the displacement at the second floor, no? The third floor, the fourth floor, the fifth floor, sixth, seventh, eighth, ninth, then 10, no? And of course at the roof, no? And then if you try to look at the maximum displacement that occurs somewhere here, so that is about 1,4, or rather 0.145, no? So 145 millimeters. But that is, no, of course, based on the design basis earthquake, no? Well, it's very obvious that considering the actual ground shaking, it seems that that maximum displacement was not reached, no? Because if you go back to the previous results of the time history analysis of the ground for the ground motion data, the maximum displacement is about 1.1 no, 3 millimeters, no, about 3 millimeters compared to about 145, which is the maximum. But of course, whether you use, we check it, the story drift, no, as prescribed in the section 208.6.5, wherein we calculate the maximum inelastic response displacement, the deltas of M, and then we compute this, and then we get the drift at the extremities of the building. So practically, even of course, no, considering the design basis earthquake, the drift values are within, no, the limit as prescribed in the code. Much more, of course, no, even for the ground shaking, or rather for the ground data that we use in the model, uh, uh, the results of the story drift check turn out to be within the limits. So again, no, comparing the two results, no, that this is for the response spectrum, wherein you have a maximum displacement of, or rather, sorry, this is from the time history analysis, wherein we have about 3.5 millimeters as maximum at the top, whereas from the time history, or rather from the response spectrum analysis procedure, the maximum displacement is about 145 millimeters. Okay, so this is just a zoom out version, view of that displacement. So as a concluding remark, this is case study on simulation of the actual behavior of the subject existing building using real-time ground motion data, and comparing results with design-basis earthquake as prescribed in the code would indicate that the existing building performed to its seismic performance level of safety, as the subject building did not suffer any major structural damage. Actually, we inspected this building, no, right after the April 22, 2019 earthquake, and we haven't seen any, not a single structural member, no, manifesting or indicating or cracks that seems to be progressing. Uh, the damage that we have observed, no, are on the ground floor, which affect only the non-structural walls, no, which are the concrete hollow block walls. So what I can say that this Midas Gen has these features, no, in doing seismic analysis, wherein you can actually make use of the actual ground motion data as an input to check the performance or the response of the building when subject to ground shaking. And this is one good feature that, in this particular project, we were able to use Midas Gen as a computing tool. So with that, thank you and have a good day. Now open for questions. Thank you.
Hello, everyone. Okay, Sir Michael. Hello, everyone. So you may now ask your queries to our presenters, Engineer Adam Abinales. So you can type your queries on the question tab or in the chat box so that we can accommodate your question. So if I may read, there is one from Engineer Ali Arqueliano. So, Sir Adam, hello, sir. Sir, you have to unmute, sir. You are muted, sir. So we're just unmuting Sir Adam in a while.
Okay, Mark. Okay.
Yes, sir.
Okay. Are you reading the questions, or you want me to read the questions? I'm looking at the question box.
You can answer some questions, sir.
Okay, sige. Okay, let me just looking at the box now. Wait. Can't hear. Okay. How about the nani? Okay. Well, definitely, the purpose of this case study is to do linear analysis. But definitely, if you would like to do the more or less accurate analysis procedure, then you really have to do nonlinear analysis. So that because of an existing building, in most cases, you really have to do nonlinear analysis so that you will be able uh, uh, to note the nonlinear behavior of the structure. Again, in this case study, we only limit it to linear analysis. Okay, there is a question here. How does the stiffness factor for beam and column 0.35 and 0.7 respectively? There is a provision in the code that would give you a table on these stiffness factors and modifiers. So I will refer you to chapter 4 NCB, which is on the structural concrete, and you will be able to see these values in that particular table. So that question is actually from Mr. Singh Ever. And the other question was from Mr. Ali or Ali Arquiliano. Okay, let me see the other questions. Wait, I'm not getting option for getting UBC as I only have IS. I think that will be answered by the Midas people, ID people.
Yes, sir.
Okay. What's this? Okay, data. Question.
Sir, if you would like, I may read some of the questions, sir.
Okay, please do, Mark.
Sir, here is from Sir Jaime Domingo. So is the time history for the three ground motions scaled to the period of the existing building, either time of frequency scaling?
Yes, it is. The time history data that we use for the three ground motions was scaled to the period of the existing building.
So another one, sir, from Sir Rensor Camacho. In time history analysis, do we need to scale the base shear, same as response spectrum analysis?
It's only in the section 208 that when you do the linear dynamic analysis using response spectrum, you do the scaling for the static base shear. No, that is for the response spectrum. For the time history, because basically in this example, in this exercise that for that particular, we actually use data, and because we know exactly because if you will note that we in the linear analysis, when we inputted the time history data, that has been scaled down already, corresponding to the response modification factor R.
So another one, sir, from Engineer Baris. Is that the PBD method, sir?
No, it's not. PBD is more on a linear. In this case, it is not a performance-based approach. Um, we are only limited to this kind of study that we have to use the NECP because there is a questions whether the building conform or complies with the provisions of the NECP. But if you are really going to do the performance based, then you will have to do further study wherein you will have to get the site-specific spectral acceleration so that you will be able to use it as your seismic parameters in doing the performance base. So this is not a PBD approach. This is still core-based.
Okay.
Okay, Mark?
Yes, sir. So some of
You
the
still have
question actually for Midas stuff. So for regarding some of the function of Midas Gen, so you can email us at phinquiry@midasit.com. So again, for this one from Engineer Jose Manuel Guzman. So sir, he is asking what's the reason for use 84 degrees not 0 and 174 by 90 degrees for the seismic action. So maybe it's just pertaining for the uh, orthogonal effect, sir.
Yeah, actually, it has something to do with the excitation angle. The Midas Gen software, I think, has that auto search excitation angle calculation. So you only have to enable it for you to be able to get more or less the excitation angle that you're going to use in your analysis. But basically, we do not know how the ground shaking when the building is hit by an earthquake ground motion. We don't know exactly what direction it will occur. So you have to do all the possible angles that wherein you will produce the worst effect on the structure. So the structure will, or rather the program, will that feature of the program will help you decide on that.
Okay, sir. So most of the question is actually for my desktop. Again, I am repeating. So if you would like to ask some of the capabilities of Midas Gen, you can email us at phinquiry@midasit.com. So last three questions, sir. So first
Okay.
is from Engineer Francisco Berin. So we know that PBD is quite difficult. When should we need to do PBD in a structure?
Okay, that's a very good question. No? Now, if you, well, I will let me just give you these scenarios wherein you need to do performance based. Number one, definitely for an existing building, and then you want to know, say, if that building happens to be a critical or an essential building, then if that is subjected to a ground shaking, then it's recommended that you do performance-based approach in a 41 as a reference standard, wherein we can do the performance-based approach, and there are some procedures stipulated in the ASC 17, and you will be guided on how to go about it. But definitely, doing the performance-based design approach for evaluation of existing builds, you will have to set some parameters. No, you define the seismic performance level, not the seismic performance objective, what the seismic hazard that you are going to consider. Then it is a very, it's not to fully understand the procedure itself. When you are designing, say, for example, a new building structure, now you can see the limitations of the using the provisions of the code, no, for certain heights of building structure. But definitely, if you talk about high-rise buildings, tall buildings, no, it seems that our code, no, won't be able to capture, no, the some provisions may no longer be applicable, no, when you talk about very tall buildings. In that case, some designers are using performance-based so that they can be able to capture the the behavior of the building when, especially when subjected to uh, earthquake, ground shaking. But definitely, again, the procedure is not that easy. So you really have to have further studies on understanding performance-based design approach. I would like to say no and recommend you that you have to take up as a any Masters of Engineering postgraduate studies to be able to do that specific on performance based. If I may refer, no, I believe we are uh, I would say, no, me personally, I am taking up this professional masters on tall buildings in AIT, and then wherein we are doing this performance-based design approach. But that would be another forum, no? If you want to know more about this, but maybe in the future. Um, as much as possible, when you are evaluating existing buildings, no, it is recommended that you have to do it using performance based. But there are some limitations. I'm sure that there are some limitations on on the understanding of this PDD. So maybe you really have to go beyond. No, I mean in terms of learning. So I hope that answered my questions to the one who raised the question. Mark.
Okay, sir. So if there are no questions, so we would like to thank Engineer Adam Abinales for sharing his knowledge and expertise in the said subject.
Thank
So
you.
that would be all, everyone. So again, if you want to send some of your queries regarding the function or capabilities of Midas Gen, you can email us at thinquiry@midasit.com. So, Sir Michael, Sir Daniel.
Thank you. Thank you very much, Sir Mark, and also Engineer Adam Abinales. Just a few
Thank you.
reminders will be, yes, sir. We'll be doing a rerun of this webinar tomorrow. For those who have missed, if you have colleagues or friends who have missed this webinar, for them to be able to continue the course, they can join tomorrow's webinar and then tomorrow's webinar for the rerun. And then those who are asking regarding the assignment, they can send the workshop assignment through inquiry at midasit.com so that it can be acknowledged by our technical support engineers. Once again, thank you very much for everyone who have invested their time and effort to attend to our today's webinar. We'll be doing the training session on Wednesday, and then another rerun on Thursday for this presentation. This has been Midas IT Philippines. Keep safe and try to minimize your activities outside. Thank you very much.
Thank you. Thank you.
Thank you, sir.